In this video, we are going to learn about the two laws given by Gustav Robert Kirchoff for current electricity. The first law called Kirchoff's first law. It's Kirchoff or Kirchoff, I don't know. The first law is called the current law or junction law. In this law, Kirchoff gave us two laws. First is the current law or junction law. Second is the voltage law or loop theorem. I don't know how they call it voltage law and loop theorem at the same time. But anyway, let's call it the voltage law. The second one is the voltage law. The first one is the current law or junction law. So we are looking at the current law or junction law. And the statement is that first let us look at what is a junction. A junction, I have not said the statement yet, so let's see the statement first. I'll write the statement. So this is the statement of Kirchoff's first law, that the algebraic sum of electric current at any junction is zero. Electric currents at any junction is zero. Now the question is, what is a junction? A junction is where the current can split. Like there is a current coming in from here, and if it branches out, there is a splitting of current. So this is the junction. This is a junction. Okay. So this is called junction. The statement is the algebraic sum of electric currents at any junction is zero. This means that if there is a junction, this point is a junction, and there are many wires here, not necessarily parallel. Okay, they are just many wires connected at this junction, and there's a splitting of current, and currents are coming in from here and going out from here. Can you see the coming in and going out? I'll draw a better diagram. Just a minute, I'll draw a better diagram. So let's say this is a junction, and here at the junction, current is coming in from these points. The blue ones are the current is coming in, and current is going out from these two. So basically, according to the statement, there should be no current at the junction. Okay, there should be no current at the junction. The current at the junction should be zero. The current at the junction is zero. So the current here is zero. That means no current stays here, no current stores up here, nothing. So let's say this is I1, I2, I3, I4 and I5. So the sum of these should be zero at this junction. So now for the junction, there is an equation taken as I equal to 0. This is the way it is taken. Obviously, sum of all this is equal to 0. Now the sign convention is that every approaching current has to be taken as positive, and the leaving currents are obviously as taken as negative. So here I1 plus I5 plus I4 minus I3 minus I2 equal to 0. That is obviously equal to I1 plus I4 plus I5 equals to I3 plus I2. This is the current law. Simply, there should be no current at the junction. The current at the junction should be 0. That is the current law. The sum of the currents flowing towards the junction is equal to the sum of currents leaving a junction or going away from a junction. And this law is also in accordance with the conservation of charge. That is, since there is no accumulation of charge at this point, there is no gain or loss of charge at this point. So all laws, there are only very few laws which are themselves basic. I mean, those laws are used to define further concepts, or there is no other base to the law than the law itself. But the other laws, like the Kirchoff's law, is based on conservation of charge. There should be no gain or loss of charge. So there is another basic concept on which this law is based. So this law is not basic in itself, if you know what I mean. Okay. So now we go. This is the Kirchoff's current law or junction law. Now we go to Kirchoff's voltage law or loop law or loop theorem sometimes. So now we see Kirchoff's second law or voltage law. There are many circuits, and this law has specifically a use in circuits. The previous law also had a use in circuits only, and anywhere else we want to use it. But this is specifically for closed circuits. And now let's get to the statement of this law. I suggest you pause and read the statement. I'm reading it out anyway. In a closed loop of electric network, the algebraic sum of potential differences for all components plus the algebraic sum of all EMFs equal to 0. And the mathematical statement for this is summation of all potential differences plus summation of all EMFs, electromotive forces in a closed circuit is equal to 0. Closed loop circuit is equal to 0. This is the mathematical statement for the given Kirchoff's voltage law. What is the potential difference? Potential difference is the drop in potential across a resistor. If we do not even put plus and minus here, if a current goes from here, it obviously passes through this resistor and goes here. So the drop in potential causes a potential difference here. So IR is basically equal to V. So it's basically as good as writing V. But this is improper. It is not as accurate as writing this and is going to cause confusion. We do not write V here, okay? So this is a potential difference. And what is E? For a battery, for a cell electromotive force is a work of a cell. Not a work, but is in a cell. This is a positive side, this is a negative side, and this produces the current. A cell produces the current in a loop, in a circuit. Produces the current basically because of its difference in charges. But we are not going to that. E is on this, is on the cell, and IR comes from this potential difference. That's why I was trying to make these diagrams. If people did not are not absolutely clear about potential difference and EMF. And now there is another sign convention in this, but first, before we get to the sign convention, we first try to draw a loop, and this time I am not pausing the video to draw the loop. I will draw it right here live. Let's say this is a loop, a simple loop. This is the loop. These are two cells here. These are resistors, and we are going to name these resistors R1, R2 and R3, and these as E1 and E2. Now we get to the sign convention. So the sign convention is that if the direction of tracing is same as that of the conventional current flow, then the potential difference across the resistances is considered as negative. See, the positive is this side, the negative this side. Again the positive this side, negative this side. Now, oh wait, I think I should simply remove this cell here from here, because I think this is going to cause confusion. So let this be E2. So this is positive and this is negative, and we know that the conventional current flow is from the positive terminal to the negative terminal, and therefore current flows like this. So the sign convention says that if we are taking in the things in the direction of the conventional current flow, then if we cross a resistor, potential difference across this resistor will be taken as negative. If we do it in the direction of the flow, will be taken as negative. If we go opposite in the direction of the conventional flow of current, it will be taken as positive. Again, for the EMFs, if we go from the negative side to the positive side, if you go from the negative to the positive side, it is positive. The EMF is taken as positive. And if you go from the positive side to the negative side, it is taken as negative. Now, first we'll write it with the signs. So it's very clear. The current flowing in the circuit is I. So now, if we begin from point A, we are going to begin from point A. This is B, C, D, and this is again A. So we are discussing about the loop A, B, C, D, A. So as we begin from A, the current flowing in the circuit is I. We begin from A, we cross R1. Since this is the direction of flow of conventional current, we cross R1 with current I and resistance R1. We write minus I R1. We reach B. From B we again go forward. It's in the same direction. We write minus I R3. We go till D, because there's nothing here, we go till D. It's again in the direction, because this is in the direction of the conventional flow. we write minus IR2, and as we cross the EMF, the convention is if we cross from the negative side to the positive side, it should be taken as simply positive. So we write E2 equal to 0. Because of this, E2 equal to 0. Yeah, E2, all this equal to 0. So this was Kirchoff's voltage law, and I think we are already out of time for this video. It's already 16 minutes, I think. So I'll take a double loop in an example video, which will be just after this one in the playlist. So please watch the example video also. And now if we take Kirchoff's voltage law, the potential difference, this voltage law is again not a basic law, not very basic in itself. It is again based on the law of conservation of energy. How? The definition of potential difference, which I showed here, is it represents the energy spent in sending a unit charge around the circuit, and E represents this summation, represents the total energy spent in sending a unit charge around a circuit, and this E represents, summation of E represents the total energy supplied by the sources of EMF in that circuit for sending a unit charge. So basically both are energy and therefore Kirchoff's law is based on the, or is in accordance with the law of conservation of energy, because this one is supplying energy for sending a unit charge around the circuit. This one is represents the total energy spent in the sending a unit charge around the circuit. I think this is the end of the video. The example for a double loop is in the next video in the playlist. Thank you.